Welcome back. Now today we are going to cover the remaining portion of the introduction to microstrip antenna, and that is basically dealing with the equilateral triangular shape. In addition to that, in this lecture we will cover some of the other shapes of the microstrip antenna, like a semicircular, a ring, all those variations which are regarded as a compact antennas. Okay, so we'll cover few of those variations also today. So let's begin with the equilateral triangular patch. This is the third variation which you are going to study of the regular shape geometries. Now, as the name suggests, this is the equilateral triangular patch where three side lengths are equal. They are equal in dimensions. Okay. Now, in comparison to rectangular patch and circular patch, the difference comes with respect to the centroid. In case of RMSA and CMSA, centroid coincides with the center of the patch. So all the field variations of fundamental mode, let it be 10, 11, they occur with respect to the center of the patch, which eventually is the centroid of the geometry. In this case, center of the patch and centroid are at a different point. Okay, everything is governed with respect to the centroid. So here at 2 by 3 from the top, that is 2 by 3 h from the top or h by 3 from the bottom, here your centroid point resides. With respect to that, modal variations are present. Okay, if I just go to the resonance frequency equation of ETMS to begin with, this is the resonance frequency equation for the equilateral triangular geometry. Here M stands for number of half wavelength variation along the side length, vertical side length, and N stands for number of half wavelength variation along the base of the ETMSA, whereas L stands for number of half wavelength variation along the height or the Z axis. Now remember, this L variation we are not going to consider because that comes in much thicker antennas, because there you need to have the substrate thickness in terms of 0.25 lambda, 0.5 lambda, those variations will eventually be seen. We are going to use substrate thickness less than 0.1 lambda, there these L variations are not considered. That's why this FMNL eventually becomes FMN. Okay, so this is the resonance frequency equation. Okay, AC is the effective side length. Now we'll go back to the geometry. So one half wavelength variation along this and another half wavelength variation along this, that is the modal identification in equilateral triangular microstrip antenna. In case of rectangular patch, the variations were considered along the length and the width. In case of circular patch, the variations were considered around the perimeter and the orthogonal radius. Remember, in microstrip antenna, modal variations are always orthogonal. Means what? There always exist two orthogonal dimensions which are perpendicular to each other, and this concept is applicable to all other regular shape geometries also. I'll take an example of that bit later to explain more about this, but these variations are there for all shapes. Orthogonal dimensions have to be considered for judging the modal variations or identifying the modal variations. Okay, so let's go back to ETMSA. This is patch side length and this is base. Fundamental mode in ETMSA is TM10. What 10 means? One half wavelength variation along side length of the patch and zero variation along the base of the patch. Now let's understand it more deeper. Here is the field point. This is the zero field line. Why? It is coinciding with the centroid. So this is the zero field line and this is the variation of one half wavelength. Now just look at the geometry. The bottom part is wider, whereas the top part is getting tapered into a vertex. Okay, so here impedance is higher. Naturally, you have to just compare here thicker wire and thinner wire. Thicker wire will have a very small impedance. Thinner wire will have very large impedance. So here impedance is very large as against impedance is very small here. I will show you the impedance chart later for the fundamental mode where these things will be more clear. Okay, so here with respect to this point the field varies 0 to plus to double plus and triple plus. These plus variations indicate the polar magnitude. Okay, indicate the magnitude. Plus maybe 200, double plus maybe 600, triple plus maybe 1000. Likewise it has to be judged. Why? Because the width is getting tapered, whereas at the bottom the width is wider, so that much variation is not possible. The bottom part variation is very similar to your rectangular part because width is almost remaining constant or increasing. So here the variation will be 0 to 200 or 0 to 150 also. That is the difference in the modal field distribution or the impedance. You must have seen the circular geometry and the rectangular geometry. What you have observed, on either side the structure was same. Because of that, impedance variation on the structure was uniform. It was not a asymmetrical geometry. This is a asymmetrical geometry. Why? Because of the nature of the structure. So first point of comparison with respect to CMSA and RMSA, this is an asymmetrical structure. Okay, asymmetrical structure creates what? Asymmetrical impedance variation. Asymmetricity also creates some kind of a higher cross polar. Why? More amount of Jx, Jy component at the fundamental mode itself you will get. In the end, we will be comparing. I will be giving you, listing down few points of comparison where I will be comparing RMSA, CMSA, ETMSA. We have one table also. There itself you will see ETMSA has the lowest gain of all three. Why? One, because of the cross polar generation. Again, those things I will explain it towards the end. Okay, so this is the impedance variation. One more catch over here. Now these are dotted structures which are there are equipotential lines. This is the centroid. Okay, so equipotential line will go like this. Now that equipotential line is at the same radial distance from the vertex. You can judge that. So zero field is like this. Fine. Similarly, 100 or 200 magnitude field is like this. 400 magnitude field is like this. On the other side will go. This is say minus 100 field. This is minus 100 field. Now look at this point. This point over here. This is the radial distance. So a corresponding equipotential point will come somewhere here. Are you getting it? The corresponding equipotential point will come somewhere here. The corresponding, like here you have corresponding equipotential point will come somewhere here. So this point may be at say minus 200 impedance. Minus means I am just showing the reverse polarity. This point is at minus 200. This was at minus 157. But this distance is shown as a double plus. This distance is shown as a double plus. That means why the length has more traveled. Because of that, if this is minus 200, this may be minus 300. Why? Because this distance, this much radial distance is coming over here. So additional distance travel, field variation is more. Field variation is more, magnitude has increased further. So that itself creates, if you go across the base of the equilateral triangular patch, there also you will see variation. What it will cause? Just imagine, here you have minus 200, minus 300. What it will lead to? It will lead to a current flow like this. It will lead to a current flow like this. So ideally the current flow should be like this, but it is tending towards like this. So earlier I have said Jx, Jy. This has created bidirectional variation. Compare that in rectangular patch where everything was horizontal. Compare that with respect to circular patch, less of a bidirectional variation was there. But here, because of this, you have more bidirectional properties. So this is the one differentiating point with respect to the field distribution of equilateral triangular microstrip antenna. Okay, so this on this point you differentiate with respect to other two geometries what we have studied. So this is about field distribution. Now let's go to the fringing fields. Now fringing field is something very important. Why? Because one can draw the magnetic dipole. Okay, so here magnetic dipole orientation may be like this. Here magnetic dipole orientation like this. So you can actually draw these magnetic dipole orientations. Now just see, the radiation pattern is not going to get fully cancelled from these two radiating slots. Why they are equal? Not they are equal in magnitude. Why? Because these, you can look at this fringing field lengths. Fringing field lengths indicate the magnitude of that point. Okay, if the more fringing field length is there, the magnitude of that point is more. So naturally, everything is not getting cancelled. Plus, you have a magnetic dipole at the bottom. That is also varying in amplitude because of this variation. So, this gives me a radiation pattern which is broadside, because they will constitute to broadside radiation pattern but not getting cancelled completely. But this component will give you some higher cross polar generation because of this bidirectional current variation. There itself the difference of radiation pattern of equilateral triangular microstrip antenna against a circular and rectangle comes. Radiation pattern has a higher cross polar because of the asymmetric structure. Okay, because of the asymmetric structure of the configuration. Okay, so this is about equilateral triangular geometry. This is a fundamental mode. Fundamental mode is TM10. Remember, in some books they also called 10 variation along the height. One variation they also called it along the height. That is also fine. But generally we say the 10 variation is along the side lengths rather than the height. Okay. So this is about equilateral triangular geometry. Now we'll go to the design aspect. How to design that equilateral triangular microstrip antenna. Okay. Now this variation in fact I was talking about. See this. This is the centroid point. This is maybe somewhere around 200, but look at the variation on the other side. So here I want to add one more point here then. See, if I want to get a 50 ohm point, it may lie at this much distance, maybe 2 centimeter from the, this is a comparative value which I am mentioning, which may be at 2 centimeter, but on the other side 50 ohm point may be represented at 8 centimeter. Why? Because the field variation depth are different. So the equi-impedance point on either side of the zero field line are present at a different distances. That is also one of the asymmetry which is present in the structure. Okay, so this is all about that distribution. Now we'll go and see, you can see that this is the cross polar. I have seen in the earlier lecture the radiation pattern of rectangular patch. How much? They were maybe somewhere here, but now they have increased. They are at least 15 to 20 dB down compared to the copolar level. Okay, much higher compared to RMSA or circular MSA. If I just go on comparing these three on the cross polar front, ETMSA has the maximum, then the circular, then the rectangular. So this is one of the comparative point. Of course, in the end towards the lecture, I will be giving a rough table where we will do all comparisons, because this can be one of the questions. Compare RMSA, CMSA, ETMSA. So following will be the points that we are going to discuss. Okay. So this is the impedance variation. Now let's go to the design. The same problem will take. Design the equilateral triangular microstrip antenna for fundamental mode of TM10 at 900 MHz on FR4 substrate. Let's go to this equation. Equation for effective side length is over here. Now again, equation for epsilon Re, just like the case which was there in rectangular patch where we have used a transmission line model, that equation, such kind of closed form equations are not available. So again, which I have discussed in circular geometry, where Zn equation is not available, similarly that is not available here also. Similarly, some kind of a closed form equations are not available. So here epsilon Re, one way of looking at epsilon Re is taking the average width along the length or the height of the ETMSA. Means what? At this point average width is 0. At this point average width is, because current are traveling like this, na? So the average width is 0 plus W or S by 2. According to that you calculate epsilon Re. That is one approach. Or you can just say epsilon Re is equal to epsilon R and calculate the value within certain 40 megahertz variation. You will get your resonance frequency matching with respect to desired value. But one way of addressing this epsilon R equation is you can use the transmission line model equation, that is epsilon R plus 1 by 2 upon epsilon R minus 1 by 2, that equation which was there in RMSA design. Okay, that here over there S by 2 can be taken as the width of the patch and you can calculate effective epsilon Re. That is also possible, but again it is a topic of research. One can work on this to find out what is the exact equation for epsilon Re, and not just for a thinner substrate but for different substrate thickness, because this is also one of the parameter which you can vary and then predict the value of that. So from rough, like with respect to the problem which I am giving you, you can say epsilon R is equal to epsilon R, or calculate with respect to the other one. Both approaches are fine. Then for the given frequency will be given, calculate AC, like 900 is given to you, 900 you substitute, or rather if you are taking C in 30, put 0.9 here, calculate AC, and from that you calculate S. Okay, so likewise you design equilateral triangular microstrip antenna for the given fundamental mode of operation. Okay, so this way you design it. This is the current distribution which I was mentioning. You can see, isn't it, a bidirectional variation is there? Why? Because you have difference of potential between the center point to the edge point. That creates the bidirectional variation, and that has increased the cross polar. Okay, this is fundamental TM10 mode. Now talking about the higher order modes, in fact in the next topic of discussion we will be dealing with the higher order modes and all those things. There, knowledge of higher order mode is something very important with respect to the designing of broadband, dual band, even circular polarized antennas. So there they are always called as the driven mode. So with respect to the feed point where you are keeping, because you can see this is a feed point over here, a coaxial probe representation is shown over there. So with respect to the feed point location, your higher order mode gets excited, of course at higher frequency region. So the next higher order mode is TM11, where you will see variation along side length as well as base. You can see that variation. In TM20, it is basically the variation along this 2 half wavelength variation along the height is observed, or along the side length. So this is how the higher order modes of ETMSA are there in comparison to the circular patch and the rectangular patch. More asymmetry is there, and more asymmetry leads to the higher cross polar, may be better for circular polarized generation. Okay, so I have explained you the equilateral triangular design. I have explained you how to design the equilateral triangular patch. Those guidelines are given. Now we will do the comparison. We will do the comparison of rectangular geometry, circular geometry, and equilateral triangular geometry for a given frequency. So I come to this part later. Okay, so here we have some comparison table where you just look at first these parts, CMSA, RMSA and ETMSA. Don't look at any other part. So the antennas are designed using this substrate parameter at the same frequency. What you will observe that again the frequency is nearly same. Gain of these three antennas RMSA has the better gain of all. Why? Because the area of the RMSA comes out to be larger in comparison to CMSA and ETMSA. So the gain is more, because as per we go with the equation of 4 pi AE by lambda square, AE is more in case of RMSA. RMSA gain is bound to be larger. Next point is, in fact you can see it over here, the area is more in case of RMSA. The bandwidth offered by CMSA, remember, is always optimum. Later on also when you do broadband designs, bandwidth offered by CMSA is more. Okay. Against that, the gain in RMSA is more. Cross polar level are higher in case of ETMSA and minimum in RMSA. That table is not over here. Cross polar level are higher in ETMSA. Again, they are very much smaller in RMSA. So if I just go from cross polar level, RMSA has the lowest, ETMSA has the highest. Okay. In terms of gain, so the comparative points will be related to the gain. RMSA has better, bandwidth CMSA has better, and cross polar level are higher in ETMSA, lower in RMSA. So if I ask you now, select one of the patches with respect to the personal mobile communication system, there what you require? Higher cross polar, because signal can come in any direction. So if the signal can come in any direction, gain kitna hai? Jara difference hai kya? No, 0.6 dB. Fine. So I will go with ETMSA. That way selection has to be done. Another question can be this way, that I want to design the antenna which should receive the signal in any direction, plus it should cover a lab like a distance. So when I say a lab like distance, that means I require a low cost solution and a low gain antenna. So FR4 will do. If I want to cover a larger distance, I require a efficient antenna. So RT-Duroid, air, foam or other kind of substrates have to be used. So likewise, by doing a proper blending of the practical applications, we can address the problem statements. Okay, so more practical approach has to be brought into this. So here we have compared RMSA, CMSA, ETMSA, three differentiating points: gain, bandwidth, cross polar level. Okay, so I have told you which are the best amongst the three. Now we will just introduce few of the compact variations which I have just said earlier, because we will do it in detail when we go to compact antennas. Now these are basically the compact variations of circular microstrip antenna. What happens is, in fact, there is a lot of big detailed topics are there on design and evolution of compact geometry, which we will do later. So here, if you look at this structure, it is basically a circular patch is there, and the symmetry of circular patch is used to create a semicircular antenna. Here we are saving 50% of the area. Okay, they work at the same frequency. Okay, they work at the same frequency. More on that we will do when we actually go to the compact microstrip antenna design. Why compact? Because size is a constraint. These are the days of miniaturization. So in miniaturization, one cannot have, what should I say, many large area allotted to the antenna housing. Not possible. Look at your mobiles. How much area you can afford? So very small area is available. Within that you need to put your antenna. So there compact design is very essential. And one of these techniques is to realize a compact patch by using symmetry of the structure. That design is semicircular microstrip antenna. Another design which I have just shown in the flow of the discussion today is the ring microstrip antenna. I'll just talk more on this over here. Okay, this is another function which is used, KXNM. Here, what is done? This is a circular patch. Inside that circular patch, you cut a slot. Because of the slot, the effective current length increases and decreases the frequency. Okay, this is another kind of compact antenna design. I am purposefully not getting into the details of this, because this we will do it in detail when we deal with compact antenna designs. Okay, similarly you will have a ring, square ring antenna design. That also is on the similar function where the length of the patch is increased. It is too early to discuss about these points, but since they are there in the flow of the equation, and these are some of the regular shape MSAs. These are some of the regular shape MSAs. Why? Because they are derived from these original three patches. Okay, they are derived from, hence I have just discussed them in the flow. So here we complete your topics related to the introduction. Okay, more detail about that you can definitely find in the first book, that is on Behel Bhartiya, the microstrip antenna design, or even chapter 1 and chapter 2 of Girish Kumar and KP Ray, where all these discussions related to the basics of regular shape microstrip antenna, their higher order modes, resonance frequency equation, and even a bit of parametric study related to the effects of various parameters is mentioned. So here we complete your first chapter. We'll now meet in the next chapter for the details about the broadband antenna design. Thank you.